So hi everyone, today I will talk about our work, entry-wise approximate solutions for SDDM systems in almost linear time. This is a joint work with Angelo Farfan and Mehrdad Gadiri. So first, I will briefly introduce the Laplacian solvers. Recall that a Laplacian matrix is D minus A, where D is the degree matrix and A is the adjacency matrix. And Laplacian system is solving Lx equals B. This has become a central primitive in graph theory. The Laplacian paradigm has led to fast algorithms for flow problems, better graph sparsification, and it also plays a role in space de-randomization. So for this fundamental problem, the classical Laplacian solver gives normalized guarantees. So x tilde is close to L inverse B under some vector norm. And the first near linear time solver was given by Spielman and Ten. In this talk, we ask for a stronger and more local guarantee, that is entry-wise guarantee. So we want to approximate every entry of the solution vector. So this is a more recent setting proposed by Gadiri, New, and Yang. They gave an O tilde M root-n time algorithm. So the question for this talk is, can we make the entry-wise Laplacian solvers faster? Then I will introduce the SDDM systems, which is a more natural setting for Laplacian solvers under the entry-wise guarantee. So SDDM stands for symmetric diagonally dominant M matrices. This is defined as a principal submatrix of Laplacian. So every SDDM matrix can be completed into a Laplacian matrix by adding an extra row and column. So this makes the row sum and column sums to be 0. And for the Laplacian matrix, the underlying graph has like n plus 1 vertices. So a useful intuition here is to think of the extra vertex as an absorbing vertex. So solving an SDDM system is equivalent to computing the absorbing random walk probability. More specifically, we define the escape probability. That is, the probability that the random walk starting from S hitting the target T before hitting n plus 1. And we can show that this escape probability is proportional to the corresponding entry of L inverse. Then let's look at the small example. This path-like example gives exponentially small escape probability. Because for every step, there is a constant probability that you're absorbed by P. And you need to make at least O(n) steps from S to reach T. And this example tells us that the solution vector of an SDDM system can have exponentially small entries and must be recovered by an entry-wise solver. So that is the main challenge of the entry-wise setting. Then we present our main result. So given invertible SDDM matrices L and non-negative right-hand side vector B, assume that the inputs are given by Pauli unbounded integers. We give a randomized algorithm with high probability outputs entry-wise approximation of L inverse B. And the outputs are represented by log n over epsilon bit floating points. The running time is just sparsity of L times 2 to the O root log n. That is almost linear time. And note that we assume that the right-hand side vector to be non-negative because we want to avoid cancellations. Our work builds on the threshold decay of the previous work, GNY26, and we only use black box access to the standard fast Laplacian solvers. Then let me briefly introduce the threshold decay. So the idea is that for large entries, we can actually convert the normalized guarantee into entry-wise guarantee. Because additive errors can be turned into relative error if the number is large. And then we can just peel off the large entries in the vector and solve the reduced system recursively. The algorithm is simply O(n) levels of systems with reducing size. And at level T, we solve the system LT xt equals BT. and we denote the large entries as ft. So the dimension of the current level is just the dimension of the previous level with the large entries removed. And we can show that the right-hand side vector bt decays exponentially. So the norm is approximately like n to the minus t for level t. This solves the solution coordinates in the range around n to the minus t. So we only need ON levels to solve all the coordinates because the smallest coordinate is at least n to the minus n. And we note that for this threshold decay framework, each level only requires a regular fixed point Laplacian solver because we can normalize everything with respect to the norm of B. And the total running time is just O tilde mn for ON levels, and we pay for OM time for each level. Then we introduce a new idea, the probability distance. We define the probability distance as some positive constant minus log of L inverse ij. So this intuitively gives the log scale reachability in the absorbing random walk. So for a large distance, it means that the reachability is very weak, and the inverse entry is like exponentially small. And for small distance, the reachability is strong. And this probability distance satisfies symmetry, non-negativity, and also triangle inequality. However, it is not a metric because generally the distance from I to itself is positive. But this still behaves enough like a distance for our purpose. And we also note that this probability distance respects the original graph structure because for adjacent vertices in the original graph, the distance is bounded by O1. This also matches the intuition that the adjacent vertices U and V can reach each other using only one step of random walk. Then our algorithm is just simply two steps. First, we construct something called low diameter covers with respect to the probability distance. And then we just run threshold decay guided by the constructed covers. The low diameter covers are just a collection of clusters where each cluster is a subset of vertices and the union is a whole vertex universe. And then we can use the low diameter covers to reduce the size of active set to just a union of relevant clusters. So this removes the small entries of the systems. And removing the small entries does not affect solving the large entries in the system. And we have the property that every vertex, once added to the active set, will be removed after D levels. So this bounds the total size of the active sets to be almost linear. And the final running time is just O tilde MD plus the size of the clusters. So the rest of the talk, we will focus on constructing a good enough low diameter cover. The main challenge here is the access to the probability distance is highly restricted because by definition, we must use Laplacian solver to compute like the entry of the L inverse. So next, we describe the low diameter cover problem. We need to construct clusters such that first, every vertex is assigned to some cluster, and the vertex has a distance gap from the vertices outside of the cluster. And second, every vertex is contained in no more than n to the little O1 clusters. This is for bounding the final running time of the algorithm. And third, every cluster has a low diameter n to the little O1. So every cluster has two parts. We use the inner ball to denote the set of assigned vertices to this cluster. And we use outer ball to denote just the cluster itself, that is all vertices in the cluster. And the natural construction for one cluster is to use the radius R balls. We use BUR to denote the radius r ball centered at U. So we can just construct the inner ball as BUR and outer ball as BU2R. So that is, we use the larger radius for the outer ball. This automatically gives the first condition, that is a distance gap between the inner ball and the outside vertices. And we observe that we can use one Laplacian solve to give the construction of one cluster, because we can use the indicator vector of U as the right-hand side vector. And this solution vector just gives you the distance from the center to all the other vertices. So the next question is, we cannot afford so many Laplacian solves. The idea is to solve parallelly. We pick a set of centers S, and we use indicator vector of the set S as a right-hand side vector. So this gives you the sum of the solution vectors for each center. And what we obtain here is actually a union of the clusters of each center. And if two clusters have intersection, then we have no idea how we can assign the vertices in the intersection part to the centers. So we can only extract the cluster having no intersection with other clusters. And note that two clusters have intersection if and only if the distance between the centers is at most 4r. So how can we pick the set of centers? We can use sampling. We sample a set S by including every vertex with independently with probability P. And for a vertex I, it is covered if there exists a sampled center within a distance of R. So that is like the vertex I lies in the inner ball of the sampled cluster. And we also need that the sampled cluster has no intersection with the other clusters. Here we can use triangle inequality. So to ensure that there's no sampled center within a distance of 5r, then the distance between the two centers is apart by at least 4r. So next, we want to prove that every vertex is covered with high probability. First, we can look at an easy version of this. Suppose that the radius parameter in the second condition is r instead of 5r. Then these two conditions merge into one. That is, within the radius r ball centered at I, there is exactly one sampled center. Then we can just use the hierarchy of probabilities. So there exists some P such that P approximates the inverse of the size of the ball. So the probability that exactly one vertex in the ball is sampled is at least constant. So we can repeat for like O log n times, and all the vertices are covered with high probability. And then for the hard version, if the radius is 5r instead of r, similarly, we still need the probability to approximate the inverse of the size of the ball, but here we need for the larger radius 5r. And then conditioned on this second condition, we have the first one holds with probability the ratio of the smaller ball size to the larger ball size. And then we can use a hierarchy of distances. So we pick root log n different radius, and we can show that there exists a ratio that is at least 2 to the minus root log n. This is because the product of the ratio is at least 1 over n. And using pigeonhole principle under the log scale, we can show there exists at least one that is 2 to the minus root log n, which is n to the minus little o1. Then we conclude with the final sample complexity n to the little o1, because each sample succeeds with probability n to the minus little o1. And the final diameter parameter is also n to the little o1. Okay, so let me summarize the takeaways of this talk. We give an almost linear time algorithm for entry-wise SDDM solving. So we first define the probability distance using a log scale random walk probability. And then we construct the low diameter covers using black box calls to the standard Laplacian solvers. And we use hierarchy of sampling probabilities and distance scales. And this covers guides the threshold decay and bounds the total size of the active sets almost linear. And finally, here are some open problems. The first one is, can we achieve near linear time instead of almost linear time? And the second one is, can we de-randomize our algorithm? The third one is, for the directed setting, can we improve the running time to be subquadratic? Thanks for listening.